Hi guys, it's Caroline. Welcome to lesson 4 of unit 1 in the Environmental Systems and Societies course. Today we're going to talk about energy and equilibria. And they're two sort of separate concepts as far as we're concerned in science in general and in this class specifically, so we're going to talk about them separately. First, talking about energy with regard to the laws of thermodynamics. So there's two laws of thermodynamics that are important to us in this environmental science class. The first law of thermodynamics states that energy is neither created nor destroyed, it simply changes form. And that's important to us because we can see it in different ecological systems. Like here, you had energy start with the sun and create these different kinds of plants. You have lemon trees on the left-hand side and tulips on the right-hand side. So the sun's energy didn't disappear, but it changed from a solar form to a chemical form. Building on that first law of thermodynamics, we talk about the second law of thermodynamics, which states that entropy of an isolated system, not in equilibrium, will increase over time. And the example of this that might be familiar to some of you guys is this messy bedroom. I'm not doing a very good job of circling it. But over time, if you are not putting in the energy to clean up your room, the entropy, the natural state of disorder in that system will take over. And this isn't the best example because this isn't actually an isolated system like we learned about in the last class, but you get the idea. The idea of entropy is important to us in our class precisely because we're not in an isolated system. So since when we look at the Earth, we have a constant input of energy from the sun, we don't need to worry about entropy increasing too much over time. When we look at the universe, the question gets a little bit different. And eventually, the sun will burn out. It's a star and it will burn out. And it will cause the thermal death of the universe. The entropy of the universe will continue to increase and increase after the sun burns out. And eventually, the entropy will overcome any state of organization that we have in our universe. Don't lose sleep over that, though, because far before that happens, the sun will expand as it dies and engulf the earth in like a ball of fiery flames. So there won't be any of us around on this planet to have to worry about that, the thermal death of the universe. We do, however, need to think about how these two laws of thermodynamics can be applied in our day-to-day life as we look at energy use in our systems, in the systems that we have around us. So I'm going to pull up a picture, and this is from the ESS textbook, the Oxford Press book, and it shows the first and second laws of thermodynamics in a model. If you look at the sun presenting solar energy, you can apply the first law of thermodynamics as that energy changes form from solar to chemical to heat at each different step of this process. And then the second law of thermodynamics can be a little bit harder to nail down. But this idea of heat production, entropy, low order energy is being produced at every level of this food chain. And that's where you see entropy entering into a natural system. Now that we've talked a little bit about the first two laws of thermodynamics, we're going to move on to talk about how they apply to equilibria in systems. So when you have all of this energy going into systems, you need to consider how the system is able to stay in balance. There's two kinds of system balance that we look at. The first is what we call steady state equilibria, where you have a system that has constant inputs and outputs, but it stays at a state of balance that's pretty much similar. Some people also call this dynamic equilibrium. The second is a little bit less common in living systems. Static equilibrium is when you have like a pile of rocks all in a big heap, and they're not going to move because they're in static equilibrium. They're balanced up against each other. If they move, it's because they fall and they've then entered into a new state of equilibria. So what's important for you to take away from this is that we usually are talking about steady state equilibrium when we're talking about living systems. Now in the next slide, you can look a little bit at some examples of complex versus more simple equilibrium. A more complex system, like this rainforest picture on the bottom, is more likely to be able to exhibit resilience, to deal with the loss of one species and still respond with a return to its normal point of equilibrium. So complexity in a system, complex, is good for the system. We want complex systems. Complex, good. I love when it makes those little things. Simple systems are closer to a static equilibria, and they are more likely to really suffer with small changes to their balance. When we talk about equilibria, we talk about feedback, how feedback affects a system. And our next few slides are going to deal with that. So when we talk about a feedback loop, we are talking about how a living system deals with inputs of energy or matter. And there's basically two ways that living systems can do that. The first is through what's called negative feedback. And negative feedback is really common in living organisms because it operates to return a system to its original state. So you have tons of negative feedback loops in your body. Your temperature is programmed to stay around a balanced state. If you get too hot, you sweat. If you get too cold, you shiver. And that's all programmed to keep you at a normal body temperature. The levels of insulin in your blood are programmed to be at a steady state. If they get too high, your body releases glucagon. If they get too low, your body releases more insulin. And that's to keep the balance in that blood chemistry all the time, because you survive best at a very specific state of equilibrium. The planet is the same way, and the planet relies on a lot of different negative feedback mechanisms. When we look at global warming, we can think about how some different inputs might be dealt with as either negative or positive feedback. So let's look at this example of rising temperatures. This is a feedback system where rising temperatures lead into a negative feedback. When the temperatures rise, ice melts, that creates more water. The water creates more clouds. That means that the sun is reflected from the outside of the clouds and temperatures fall, allowing the global temperature to remain at a pretty set point. That's the best case scenario. But there's also a possibility that something a little bit different would happen with rising temperatures. Something that we call positive feedback. So a positive feedback loop is basically the opposite of negative feedback. It changes a system to a new state of balance. You can remember that positive feedback loops are usually bad. You don't use them in your body. We don't like to see them in climate change scenarios or ecosystems because we don't want this new state of balance. That is not desirable. We want to keep the state of balance that we know works for the system. But this same scenario of rising temperatures could lead into a positive feedback loop. Rising temperatures leads to melting ice, leads to a dark surface exposed, which means that that dark surface captures more heat from the sun, and that causes temperatures to keep rising. This keeps happening until, before you know it, all of the coastal land in the world is inundated with water because so much ice has melted. So when we think about systems and models to represent climate change, the problem is that this scenario is so complex. It has so many possible systems and models that can be used to represent what might happen that it's difficult to make an accurate prediction about how and if we are going to be able to maintain equilibrium, which I think is worth keeping in mind as you consider different climate change scenarios. For now, we're going to talk a little bit about what might happen in terms of resilience and tipping points as we look at different climate change scenarios. So when I talk about a tipping point, it means the point at which you enter into a new state of equilibrium. When you think about tipping points in your life, maybe it was when you moved, or when you passed a big test that you were studying for, or when you won a big soccer game. All of those things can tip your life into a new state of balance. We don't usually want that to happen in ecological systems. And when we look at ecological systems, we can represent them with a model like this. An ecological system, or your life as a system, has a certain amount of resilience. If this is you before you passed your big test, it might be that the test isn't serious enough to tip you into a new state of balance. You stay here. You're still in high school. Maybe high school is your state of balance. But eventually, you are going to pass an important enough test. Maybe it's the SAT, maybe it's your IB exams, that you are going to tip into a new state of balance. And after that, your life will never be the same anymore. So when we look at ecological systems, we look at two things. We look at where they might tip, where they might shift into a new state of equilibrium, and how resilient they are to that change, how much they're going to be able to stay in their current state before that shifting takes place. There are some really important tipping points in ecological systems, and we're going to go over a couple of those now. So the first really important tipping point that we can look at is in hydrosphere systems, in systems that involve water, and it's a process called eutrophication. So the process of eutrophication, and you can see a good example of eutrophication in this picture on the right. The process of eutrophication is when fertilizers start to get into a water stream and encourage plant growth to a point where all other life dies out. And when you look at a hydrological system, there's a point up until which the system can resist this change of all the other life dying out. If you get just a little bit of nitrogen fertilizer pollution into a body of water, you can normalize it and it can stay in this state of balance. But once you get to a point where the entire surface of the water is covered with this algae growth, you're not going to be able to negate the effects of that type of algal bloom for very long. And that's when you start looking at a tipping point. The problem with eutrophication is once you get to the tipping point, all of the plant life below the surface dies out, and then you head in to a new state of balance that's called a dead zone, and that's not very advantageous because that means everything in the water is dead. So eutrophication is one important tipping point in ecology. Another important tipping point in ecology is when organisms in an ecosystem go extinct. And obviously, extinction represents a balance into a new state of equilibrium because once an animal is extinct, there's no bringing it back. You're in a new state of balance. Well, let's look at an example of what could happen in an ecosystem if an animal goes extinct. The example that we're going to look at is the African elephant. And the extinction of that animal would change the whole landscape of the African savanna. Because when elephants go around in savanna landscapes, they help with seed dispersal, their tusks dig for water, so they aerate the soil, they pack down soil because they weigh so much. And if those animals weren't there to do that, there would be different plants growing and totally different ecosystems emerging in these savannas. And that would be a good example, that extinction, of a tipping point for that ecosystem, where it would start to look totally different because it existed in a totally different way. So, for the homework assignment this class, we're going to do something a little bit different. Since it's really important to be able to use concise vocabulary, if you have the textbook, the Oxford Press Environmental Systems and Societies book, you should go ahead and read 1.3, which is all about energy and equilibrium. And then use the vocabulary words, the concise, specific vocabulary words that we've gone over in this lesson to try to define the phenomenon that are listed in this table. You have this as a worksheet also. And try to define them in as few words as possible. There should be like 1 or 2 word defining terms for all 5 of these. So take a look at that, look back through the material if you need a clarification on anything. When you're ready, you can check your work in the review video, and I'll see you there.